Hello, everyone. Today's recording is going to be covering Monday, Tuesday, and Wednesday of this week. So that should be January 25th through January 27th. On January 25th, I was actually out of class that day. So the only assignments that you students had was to complete a preview of Newton's laws in your bell ringer. So I am going to go over the bell ringer here. So in the bell ringer, it says, Susan gently pushes the tip of her finger against the eraser on her pencil, and the pencil does not move. Which of the following figures best illustrates the interaction of forces between Susan's finger and her pencil? We are now in third quarter, and we are going to be talking about Newton's laws of motion. And these laws of motion describe how objects move and what types of forces they exert on each other and how those forces impact or change the motion of an object and even the direction. So one thing I want to point out is that anytime we're looking at forces, we use a vector or an arrow to designate them. So that's what these arrows mean. Secondly, all objects in the universe exert a force, regardless of their size. So the smallest grain of sand to the largest planet, all of them exert some type of a force. So if you're showing forces of objects, every single object in the diagram must have an arrow or a vector that shows the direction. So based on that information, we can go ahead and eliminate A and C because it's only showing one force here and one force here, and that's not the case. So now let's take a look at B and D. Both of these have arrows illustrating forces. Notice though in B, this one is a little larger and this one's smaller. Whenever you're looking at vectors or arrows that represent forces, the larger the arrow, the larger the force. So in this example, this arrow is larger, this one is smaller. These two are the same. So now that we've established that, we need to look at the statement. It says here, the pencil does not move. Well, if an object is not moving, then the forces must be close to being equal. So based off of that, the most appropriate and best response for this is actually D. Notice in D that the pencil is exerting a force towards her hand, and her hand is exerting a force towards the pencil. But because these two are equal, that means that this pencil is not moving. So the correct answer is, in fact, D. If B were the scenario, then the larger force would actually cause the pencil to slide in this direction. So now that we've gone over that bell ringer, I'm going to go ahead and move into Tuesday's folder. Again, this introduction Nearpod is just a preview of the things we're going to be learning about. So in your own time, you can log in and do the student paste and just kind of look at those assignments. So on Tuesday, January 6th, we had a couple things that we looked at. We watched a video from Newton's first law of the NFL. I'll share that with you in just a moment. And then we also did some direct instruction, and students were to complete guided notes. So before we watch the NFL video, I'm actually going to go through this presentation here. If you were out of class, you need to make sure that you click on guided notes. Students who were in class, put these in their notebook. Students who are virtual at home should click on the assignment, open up the Google Docs, and when it opens, you will see spaces for you to fill in your guided notes. So this corresponds directly to the PowerPoint presentation that I'm going to go over with you now. So give me just a minute and I'm going to get that PowerPoint up. So this is the PowerPoint for direct instruction that is embedded in Schoology. So if you want to listen to the lecture and then go back and fill in the notes, or if you ever want to go back and take a look at the PowerPoint, it is available to you. So let's talk a little bit about Newton's first law of motion. So the first thing I want to do is define what we call a force. And a force is basically a push or pull on an object. For objects to move, there must be forces applied. And that's basically a push or a pull. Some common examples of forces that we've actually encountered, even if you haven't ever thought of them, are gravity, electricity, magnetism, and friction. Gravity is the attractive force or an attraction between objects. So for example, the moon stays orbiting Earth because of the gravitational pull. Objects on Earth fall because of Earth's gravity. So gravity is considered an attractive force. The next example is electricity. It is in fact a force, and that's why static electricity will actually pop or make a sound or hurt you if you have static and you touch metal. Magnetism is also a force, and if you've ever taken two opposite poles of a magnet and stuck them together, you have felt this force. And the last one down here in the corner is gravity. Gravity is a force of repulsion, or a force of two objects touching that repel each other. So friction, for example, your tire on a bicycle between the road is friction. Car tires on the road, there's friction. When you're playing basketball or running, there's friction occurring between the surface of the ground and the bottom of your shoe. So these are four common forces that we experience. So where did all this stuff come from? Well, Sir Isaac Newton. Sir Isaac Newton made observations and described the three laws that we are going to be discussing over the next few weeks. Of course, now we're focusing on Newton's first law, or the first law of motion. First law of motion, what is it? Well, an object at rest remains at rest, and an object in motion remains in motion unless acted on by an unbalanced force. So objects will continue to do what they're doing unless an unbalanced force acts on them. So a book on your shelf will stay there unless a force, you pick it up, push it, or something like that. An object in space, an asteroid, or a meteor will continue to move in the same direction, in the same path, unless it is acted upon by a force. But the term inertia is directly linked with Newton's first law, and sometimes this is even called the law of inertia. But inertia is the tendency of an object to resist a change in motion. So objects typically want to remain in the state that they're in. So let's think about this for a moment. If you take a golf ball on a tee, if you put a golf ball on a tee, it's going to stay there, possibly forever, unless you hit it, the wind blows it off, the ground vibrates or something. Otherwise, that golf ball will just stay on the tee, meaning the golf ball's inertia is resisting a change from its stationary state on the golf tee. But once it's in the air, it's not going to stay that way forever. And that's because there are unbalanced forces acting on it. So when you hit a ball, like a golf ball, into the air, it eventually falls. Why? Well, one, because of gravity, an attractive force, and because of friction. So remember that air, the atmosphere around us, is made up of particles. And sometimes we refer to this as a fluid. So fluid friction of the ball moving through the air. So it has friction occurring at the surface between the ball and the air particles, and then there's also gravity pulling downward. That's why eventually it will curve, will make a big arc, and eventually curve down to the ground. But if there was no friction and there was no gravity, the ball would continue in the same direction, at the same speed, with the same velocity, and it would never stop. So a way to think about inertia, this is something you've all experienced. You're in the car riding along, and suddenly somebody pulls out in front of your parent or guardian or your brother or sister, who's ever driving, and you hit the brakes, or they hit the brakes. When they hit the brakes, the car stops, but you continue to go forward. Luckily, hopefully, you have your seatbelt on. That's inertia. You are an object moving at the same speed of the car that you're in. The car stops, but you, an object that has mass, that has inertia, resists the stop, and you continue to move forward. That's also why when somebody makes a sharp turn, you kind of go to the side. So if somebody turns sharply to the left driving a car, you typically go towards the right. Again, that's because your body as an object is resisting a change in motion. So how is inertia related to mass? Well, the larger the mass, the larger the inertia. So the bigger an object, the more inertia it has. It's going to take a lot more force to move a passenger bus than it does to move a small smart car. How can we determine forces on an object? Well, we can determine what's called the net force. And the net force is the entire force acting on the object. And we can actually calculate this. The net force will determine if the object will move in what direction. So what is the unit for forces? Well, because Newton coined all these terms, the Newton, designated with a capital N, is the force that goes along with it. So you would say 5 newtons or 5N, or 25 newtons or 25N if you were recording a measurement. So let's take a look at this. How do forces act? Well, in this example here, there's a cart. there's a force on the back and a force in the front. So you can imagine someone in the front pulling the cart and someone in the back pushing the cart. So how can we determine the net force in this example? Well, because the person pulling in the front and the person pushing in the back are going in the same direction, we add it all up. So 12 plus 8 gives you 20. And you would say 20 newtons is the net force, and you would show movement to the left because that is the direction the cart will move. What if it's the opposite? In an opposite, you have to subtract. So here's a soccer ball. Imagine someone kicking towards the right, 12 newtons, and someone kicking towards the left with 8 newtons. So because these forces are going against each other, you must subtract. So 12 minus 8 gives you a total net force of 4 newtons or 4N, and the object would move to the right because that's the direction the larger force is going. Sometimes forces cancel each other out. And if this happens, the object does not accelerate and the object does not move. So for example, if you and your friend are both pushing on the door with the same force, nobody's going anywhere. The door is going to stay in place. So what terms can we use for this? If you have 2 or more forces exerted on an object and they cancel each other out, then that is called balanced. And the overall net force is 0. So if you go back to the door example, if each of these boys were pushing on the door with a force of 50 newtons to the right, 50 newtons to the left, 50 minus 50 is 0. So you would have a 0 net force, and you would say that these are balanced because nothing is happening. What about when things move? We call this unbalanced forces, meaning they don't cancel each other out. So if it's an unbalanced force, the net force is not 0. It's going to be at least 1 or greater. So in an unbalanced force, the force will be greater than 0, and the object will move in some direction. So for balanced forces, they do result in a change in what we call velocity. So a still object will never move without unbalanced forces acting on it. So a book on a shelf is never going to move unless you go and move it, or the building shakes, or the shelf collapses. A book sitting there is still exerting a force downward, and the shelf is exerting a force upward. So the two forces cancel each other out, and the object stays still. But if you put a force to it, it will in fact move. A moving object, on the other scenario down here, will never stop moving without an unbalanced force. So what is an example of this? Well, think about the space shuttle. Once the space shuttle takes off using rocket boosters, force, right? Jet fuel is a force that helps it, or rocket fuel is a force that helps it escape Earth's gravity. Once a rocket is in outer space, beyond Earth's gravitational pull, beyond the force of Earth, that rocket ship can turn off the engine and it will continue moving in the same direction at the same speed with the same velocity unless an unbalanced force acts upon it. Okay, so that's it for that PowerPoint presentation. And so I'm going to go back in. I'm going to go back to your course. And I'm just using fourth as an example. And I'm going to go ahead and share a quick video with you now so that you guys all have the opportunity to see this. So this says Newton's first law in the NFL. All right, so hopefully you guys found that interesting, and this does a really good job of kind of relating Newton's first law to things that you may have observed. So, you know, maybe you've never actually thought about it, but the NFL and football games in general, sports, contact sports, are related to physics, Newton's first law of motion. All right, so now I'm going to go back to sharing Schoology with you. So for Tuesday, here's our folder here. We've gone over the bell ringer. We've gone through the PowerPoint. The last thing that you should do is you need to make sure that you complete your guided notes. Okay, and you can disregard the Exploring Newton's First Law. We're going to come back to this at the end of the week. So now let's move into Wednesday's folder. So for Wednesday, we have a bell ringer, a review Nearpod, and then an activity where we calculate net force. So what I'm going to have you do, I'm going to go over the bell ringer, and you need to make sure that you go into the Nearpod during your own time and watch that review. Okay. For this class, there is a quiz scheduled on Thursday, January 28th. You need to make sure you complete that in Schoology. So for this bell ringer, let's take a look. The picture below shows a student pulling on a rope that is attached to a wall. Which statement correctly describes the amount of force applied by the wall as the student continues to apply 250 newtons of force? Well, one of the things I want you to notice is that the student is pulling and the wall is not moving. So what that means is the force has to be equal or potentially more than what the student's exerting. So based off that, it says the wall pulls with a force of 125 newtons. Well, that would be less than the student, so we can eliminate A. D says the wall exerts no force because it is stationary. We can delete that as well or get rid of that because all objects, regardless if they were in motion or not, any object that has mass exerts a force. So that leaves us with B or C. It says the wall with a force of pulls with a force of 250 newtons, and the next one says the wall exerts twice as much force as the student. Well, we can't really determine if it's twice as much force. So we're just, the best, most appropriate response would be the wall pulls with a force of 250 newtons against the student. So once you've completed your bell ringer, go back into the main page. You will need to complete the student pace Nearpod at the bottom. This Nearpod goes through a review video and has a few practice questions embedded. It's only about 7 minutes long, so you need to make sure that you complete that on your own time. Now, the next activity I want to get to is the calculating net force. So when you click on that, it's going to come up two things. There's a PDF at the bottom, and there's also a Google slide. In-class students did these in their notebook. We worked through some examples as a class, as a group. Virtual students submitted this using the Google Slides. The reason why I've included both is because some of the questions are a little blurry in the Google Slides, and I'll show you what that looks like. So here they are. You can see the questions get slightly blurry. So what you can do is pull up the PDF and look at the example, but then you can type your responses in the Google Slides and submit. All right. So now that we've looked at that, I'm going to go ahead and open up this PDF document here so that you guys can see what it looks like. When it opens up, you are only responsible for numbers 1 through 10. So for the PDF, that's just the first 2 pages. So what I'm going to do now that you know where the assignment is and what you need to do, I'm going to stop sharing my screen and I'm going to come back to my camera and I'm going to go through the first few examples with you. Again, you have the PDF and you have the Google Slides. That is where you are going to submit your questions, type your answers in and submit those for a grade. But you are only doing numbers 1 through 10. So I'm going to stop sharing now and I'm going to get ready to come back to my camera in just a moment. All right, so what I'm going to do now is I'm going to work through some of these examples, probably just the first 4 to kind of guide you. And then you can go back in and work through the rest of those. Remember, you need to make sure you get these done and practice these because you have a quiz assigned for January 28th. Thursday, January 28th, you will have a minor quiz on this material. So let's take a look at number 1. So for number 1, it says there's one object and there are 2 forces being exerted. So for this, the instructions are a little different on the worksheet because it tells you to calculate the force and to circle some stuff. That's not what you're doing. All you are doing is simply calculating the net force and telling me the direction the object will move. So let's take a look. This goes along with number 1. So here's my object, and I just like to sketch a box or something real generic. But there are forces coming from the left and forces coming from the right. And when you look at the numerical value of the force, you will notice that there are 5 newtons. 5 newtons. Now, I told you in the lecture that was in the PowerPoint in Tuesday's folder, anytime you have forces that are in the same direction, equal and opposite, so these are equal in terms of the numerical value or the strength of the force is equal, and they're coming from opposite directions, they cancel each other out. So 5 cancels 5 out. So that leads us to the net force, and I'm just going to abbreviate this as NF. Net force is equal to 0 newtons. Okay, so that's 0 newtons. And because of this, this object is not moving. And we can take it a step further and say that these are considered balanced forces. So when forces are balanced, objects do not move. They stay where they are. So that's number 1 from your worksheet. Let's move on to number 2. Number 2 shows us an object with 2 forces acting upon it. So here's the object. We have one smaller force, which is 3 newtons, and we have a larger force that is 5 newtons. So both of these forces are acting on the object. They're also going in the same direction. So that means that the net force is going to be moving towards the right. So you can go ahead and kind of establish that. The net force is going to go towards the right. Because these are in the same direction, we will add them up to calculate the net force. So NF is my abbreviation for net force. It's going to be equal to 5 plus 3, which is 8 newtons. So this object is going to move to the right because of a force of 8 newtons. And we could say these are going to be unbalanced. And the reason why it's unbalanced is because the object is actually moving. And again, for forces, we always show the strength, the newtons, and the direction. So this is 8 Newton force, and the object will move to the right. So that's number 2. Let's take a look at number 3 on the worksheet. Number 3 asks you, which team will push the box further? So for this example, you have 2 objects, 2 scenarios, team 1, team 2, when you're comparing. So we're going to have team 1 and team 2. So team 1 scenario, here's our object. Team 2, here's our object. So for team 1, what I'm going to sketch is and then team 2. So in my scenario here, this is team 1 and this is team 2. So as you're looking at it, team 1 has one object and there are 1, 2, 3, 4 forces. 3 on the left side and 1 on the right side. All of these forces are 5 newtons. And again, you guys can look at this on your example. All of these are 5 newtons. So anytime you have equal and opposite forces, they're going to cancel each other out. So that means that, let's just say this 5 newtons and this 5 newtons cancel each other out. So we basically don't count them. So now if we calculate the net force of this particular scenario, 5 plus 5 would be 10 newtons, and this object is going to be moving towards the right. Okay? For the other scenario, it's simpler. In team 2, it's 12 newtons to the right. So 12 newtons is the net force. That's the only force acting on it, and it's going to move to the right. So now that we've established that, the question asks you which team is going to push the box further. Well, team 2, because team 2 has a larger force, stronger force of 12 newtons. So 12 newtons is more than 10 newtons. So the box would move further. Okay, so that's numbers 1 through 3. These are some pretty good examples. You are only responsible for numbers 1 through 10. What I'm going to do now is I'm going to actually move down and go over number 10 at the very bottom of the page. So I'm kind of skipping down. We've done 1, 2, and 3. Let's look ahead at number 10. Number 10 has a few things going on. So there is an object here, and then that object has forces coming from several directions, basically every direction. So every direction on this object, there is some type of force. So coming from the top and the bottom, there's a force of 2N. Coming from the right side, we have a force of 5 newtons. And then on the left side of the object, there's 6, 7, and 8. 6, 7 newtons, and 8 newtons. So now what we can do is we need to figure out the direction, and we need to figure out the net force. So remember, equal and opposite forces cancel each other out. So these 2 Newton forces here are basically going to cancel each other out. That means now we can calculate the net force. So on this side, 5 plus 5 is 10 newtons. And on this side, we have, let me see, 21 newtons. 8 plus 7 plus 6. So there's 21 newtons on this side. Now we have to look at the difference. Because these are unbalanced forces on either side, we're going to subtract. So we're going to take 21 minus 10, which should come out to be 11 newtons. Okay. So the net force for this example, number 10 on your worksheet. Okay, this is number 10, problem number 10. The net force is 11 newtons. And because this side is larger and this is the side the net force is on, the object is going to move that direction, which means it's going to be pushed towards the right. Okay. All right, so now that I've gone over a couple of examples, you guys should be able to work through the rest of the worksheet. So we have done numbers 1, 2, and 3, and I've done number 10. That means you are responsible for 4, 5, 6, 7, 8, and 9. And you're applying the same steps and the same approach that we did here to each of those problems. So I'm going to go back to Schoology one more time and kind of show you guys what you need to make sure that you get done. So this lesson, again, was kind of covering Monday, Tuesday, and Wednesday of this week. So when you're in Wednesday's folder, we've done the bell ringer. We've done calculating net forces. We've already done some examples, so you need to finish typing in your answers in the Google slide and submit to me. Remember, the PDF for the assignment is also embedded if you prefer to use that. The last thing that you need to make sure you do is you need to do the Nearpod for Newton's first law review. If you missed class, you will obviously need to do the student-paced version because I'm not going to be here to go through every single slide. Okay, so you need to do the student-paced review, and if you're in 4th period, at the bottom of the page, and I'll go ahead and show you guys this, these are the correct responses for the rest of the worksheet. So if you want to go back and check your work, it just shows you the answers. Again, these are just pictures I took of my worksheet, so you can kind of go back and check. And even if you're not in 4th period, you can pause the video that you're watching now, and you can take a look. So this is page 1, or most of page 1. And we've done 1, 2, and 3. So here's 4, number 5, number 6, 7, 8. Here's number 9, and we've done number 10. All right, so the last thing that you need to make sure that you do, let me go back to my screen one more time. For Thursday, in Thursday, you will have a bell ringer. And then you need to make sure that you complete Newton's first law quiz. This is your first minor grade for third quarter. All right, that's it. Again, this video covers Monday, Tuesday, and Wednesday. Thursday is a quiz day. Have a fabulous day, and I hope to see you guys in class. Bye, everyone.